Hello and welcome to this presentation on our short paper. Our short paper is titled Simple Techniques for a Novel Human Body Pose Optimization Using Differentiable Inverse Rendering. It is authored by me, Munkhtulga Battogtokh, and my PhD supervisor, Dr. Rita Borgo from King's College London. Now, let us start by introducing the problem of our work. We work on the problem of human body 3D reconstruction. In general, 3D reconstruction refers to the problem of modeling a physical object in 3D space. This is an ill-posed problem due to the fact that multiple 3D scenes may correspond to the same 2D image, an issue which we refer to as 2D ambiguity. Human body 3D reconstruction is therefore challenging, especially when we consider the relative complexity of the human body and all of its possible configurations. In this work, we focus on the particularly challenging in-the-wild images from the combat sport of judo. In judo, we can observe extreme and rare poses that have not previously been captured in the dataset. For instance, we may find poses that are upside down, intertwined, with extreme arches, or twists. As we will see, the rarity of the poses motivates an alternative to the existing methods. The existing 3D reconstruction methods are either domain-specific to human bodies or, on the other hand, domain-agnostic. Domain-agnostic approaches, as the name suggests, can be used to model all types of 3D shapes. On the other hand, domain-specific approaches may use prior data to constrain the plausible body shapes and poses to specific domain of physical objects, such as the human body. Starting with the domain-agnostic, stereo vision is the first approach that we consider. It infers depth information from multiple views of a scene. In theory, it could be used to capture all types of shapes along with the surface details, like the color. However, in practice, this approach has a high requirement on both the quantity and the quality of the input. In other words, we need many images of high quality in order for stereo vision to work. Unfortunately, multi-view images of a judo scene are expensive to obtain. Only in 2019, for the first time, did we ever experience judo in multi-view. The World Judo Championship that year used the 4D replay system, using 110 cameras to capture the most spectacular moments in judo and inspired our work. But even with more than 10 multi-view images from the 4D replays, each of which are in 1080p resolution, we were still unable to produce any intelligible results using open source stereo vision applications. For instance, the screenshot on the right of the slide shows our failed attempt with such an application called Measroom by Alice Vision. The output is on the right side of the image itself, and it is unintelligible. Therefore, we considered another domain-agnostic approach called inverse rendering, which refers to inferring 3D scene parameters such as shape and material from a single image. Within this approach, researchers have recently developed gradient-based solutions that use differentiable rendering. For instance, Lee et al. In 2018 introduced Retina, which is a ray tracing package that renders 3D scenes to 2D images whose pixels are differentiable with respect to the scene parameters. Using Retina, it is possible to optimize an initial 3D model's geometry, which is a scene parameter, against the target image. We can do this by simply rendering the initial 3D geometry into a synthetic 2D image with Retina, calculating a scalar error based on the difference between the target and the synthetic images, and finally backpropagating that error back to the geometry of the model. Remarkably, this results in the optimized model geometry looking incredibly faithful to the target image as far as at least one rendering setting is concerned. However, rendering with another setting reveals that the optimized model, in fact, is unintelligible. Body shape constraints have been violated, and the shape can no longer be recognized as a human body. This illustrates the aforementioned challenge of 2D ambiguity, which is that the same 2D image can correspond to multiple 3D scenes. The differentiable inverse rendering approach therefore needs to be constrained further. Moving on to the domain-specific approaches, we have learning-based human body reconstruction. This approach uses prior data to constrain the likelihood of parameters such as shape, pose, and color to those plausible for a human body. For example, Wang et al. Introduced Arch, an end-to-end framework to reconstruct a clothed human from a single image using learning. This work can reconstruct key surface details like clothing. However, as the authors showed with the image on the right, rare poses that are not covered in the training dataset, such as kneeling, which is common in judo, are challenging for Arch. And this is just an example of the general limitation of the learning approach. Learning requires training data, which unfortunately is expensive to obtain for real human bodies in 3D, especially for dynamic movements such as those in judo. For another learning-based example, Jackson et al. In 2018 found that they were able to reconstruct only coarse geometry using their learning-based volumetric regression technique. So they had to resort to building their own high-quality dataset, which however only included examples with restricted poses. As Huang et al. And Jackson et al. Have exemplified, learning methods often do not generalize well to data that is rare in the training datasets. This means that the variety of the poses in the training dataset, or more precisely, the lack thereof, can become the bottleneck to the performance of learning methods. Finally, the last domain-specific approach is parameterized body model optimization. In particular, we consider the work Simplify X by Pavlakos et al. From 2019. In Simplify X, a human body 3D model is parameterized by and differentiable with respect to certain parameters. These are shape, pose, and fashionable expression, denoted beta, theta, and psi, respectively. These parameters are optimized against a single target image, the process of which we shall now describe. The main data term of the optimization's objective function is calculated by reducing the target image to a 2D pose estimate, making a 2D projection of the 3D model, and comparing those two together to calculate the reprojection loss. Simplify X does not directly rely on learning, but it is still limited by prior data biases because it uses a learned body pose prior that discourages rare poses during the optimization. Furthermore, the reliance on a reduction of the target image to a 2D pose estimate is another limitation. That is because the estimates can often be faulty, and Simplify X then optimizes against those faulty estimations, which means that the best possible results will be faulty too. Moreover, the reduction of the target image makes Simplify X blind to details like clothing, hair, and color. Therefore, the quality of the 2D pose estimate is the bottleneck to the performance of Simplify X. Ultimately, this is also caused by the rarity of the judo poses because the pose estimation, which is done by Open Pose Library in Simplify X, is also done through learning and fails to generalize outside the training datasets. To summarize the limitations of existing approaches, the domain-agnostic methods are under constraint, while the domain-specific methods are challenged by the following: rare out-of-distribution poses, bottleneck due to reliance on 2D pose annotation, and blindness to other features. Therefore, we contribute our own novel optimization scheme. It combines domain-agnostic and domain-specific methods. It relies directly on source image rather than on 2D pose estimates, and it bypasses prior data bias bottleneck that we have identified, which means that even rare poses can be modeled with our approach. More specifically, our novel scheme combines the previously introduced works Redner and Simplify X together. To see how this is possible, we formalize Redner and Simplify X within the context of our novel scheme as follows. As the equation on the left shows, Redner produces a synthetic image denoted I based on scene parameters phi, which includes model geometry denoted phi geometry and camera pose denoted phi camera. As the equation on the right shows, in our optimization, the model geometry is identical to the parameterized body model that Simplify X outputs. These equations show how Redner and Simplify X can be combined together. To put simply, the output of Simplify X is pipelined to Redner as the input. Then, the synthetic image I can be compared with the target image I targets to calculate a scalar loss L for the objective function. But it is not sufficient to simply do conventional inverse rendering on top of Simplify X, that is to optimize the phi geometry parameter directly. The reason for this was already explained when we introduced the limitations of inverse rendering. Due to 2D ambiguity and under-constrained nature of the approach, optimizing the phi geometry parameter directly results in a deteriorated 3D model that violates human body shape constraints, even as the 2D rendering or the synthetic image I improves. This is why we contribute our first technique called Upstream parameter optimization. In this technique, exploiting the fact that both Redner and Simplify X are end-to-end differentiable and the fact that we pipeline the two methods in our scheme, we backpropagate the inverse rendering error all the way up to the body pose parameter denoted theta body. In theory, it is possible to calculate the backpropagated derivatives thanks to the chain rule we see in the slide. In practice, these are simply computed with automatic differentiation, since both Redner and Simplify X are implemented in PyTorch. Doing so optimizes the phi geometry parameter through its upstream parameter theta b rather than directly, and gives us the opportunity to utilize the constraints already built into the parameterized body model of Simplify X, thus alleviating the under-constrained limitation of inverse rendering. Furthermore, optimizing against the target image directly is how we also bypass the limitations of Simplify X, namely the reliance on 2D pose estimation and its blindness to features besides the pose. The final objective function in our novel scheme therefore minimizes the body pose parameter theta b and an additional parameter alpha that is custom defined to optimize the camera angle without affecting the camera distance. Note that an additional term denoted e is added to the objective function to constrain the body pose towards the neutral with a strength factor denoted with lambda. In this work, we obtained our results by optimizing with two stochastic gradient descent optimizers for 200 iterations with momentum 0.9 and learning rates 10 to the power of -4 and 10 to the power of -8 for the pose and camera angle parameters respectively. Now, we will finally describe our last contribution, a novel technique we call selective inverse rendering. First of all, it is motivated by the need to optimize the selected part in isolation from the rest. For instance, when we do not want to change a part that is already in the right position, or when the inverse rendering has adverse effects that we would like to prevent on a certain part. In accordance with the latter, the example image on the right is highlighted at the upper body part because it has been affected more adversely than the lower body. With selective inverse rendering, we would be able to control the optimization to only the desired part, in this case the lower part of the body, as we just said. Our simple and intuitive technique works by selecting by looking, which means to set the camera pose parameter such that only the part to be selected is visible in the rendering. As demonstrated here, by rendering only the selected part, it is possible for the other parts to remain unaffected, as we can see on the highlighted images on the right. By selectively rendering only the lower body during the optimization, the lower body alone has changed while the upper body has remained untouched. In theory, this is possible because of how the rendering algorithm works. By definition, a part of the model that is not visible in the rendering camera does not contribute to any pixel in the rendered image. Conversely, only the parts that are visible in the rendering contribute to the image. Therefore, parts that are not visible in the rendering get no share of the error and remain unchanged, while only the parts that do contribute change due to backpropagated error. Now that we have described our contributions, let us finally see the results of using our techniques on the challenging in-the-wild images of judo. Our results are on pre-processed judo images made public by the International Judo Federation on YouTube. One thing to note is that although the in-the-wild nature of the images and the rarity of the poses within them motivate our work, these also mean lack of any annotations and limited possibilities for evaluation. Nonetheless, we report both qualitative and quantitative improvements over the baseline methods and the concurrent work. Starting with the qualitative results, we can currently see the target images in the first column, the initial 3D model in the second, the initial error in the third, the 3D model after our optimization in the fourth, and finally the final errors in the last column. By comparing the initial errors with the final, we can observe clear qualitative improvements, such as more hunched pose in the first row, twisted legs and raised arms in the second, and raised right leg in the third row, all of which are more faithful to the target and crucial to identifying the correct judo moves that characterize the scene. We also report quantitative improvements over both the Simplify X baseline and the concurrent work by Gupta et al. 2021. We evaluate with normalized L2 normal reprojection error, like Huang et al. 2020. And we find that our method achieves up to 45.5% error reduction from Simplify X and up to 22.3% error reduction from the concurrent work. We also make the same comparison for a result using both upstream parameter optimization and selective inverse rendering. We achieve 21.3% reduction in error for the lower body from the non-selective Simplify X baseline and 18% reduction from the Gupta et al. Qualitatively, we can observe more accurate lower body pose in the selectively optimized model compared to the baseline model, as we can see from the better overlap in the highlighted images. Importantly, this is with intentionally less change in the upper body, as we can see from comparing the upper bodies in the highlighted images. The selectively optimized model's upper body is less dramatically changed than that in the non-selectively optimized model. Note, however, that the upper body is not fully isolated from the lower body, due to first, the regularization term in our objective function that brings the pose to the neutral, and second, the lack of disentangling in the pose parameter embedding that we adopted from Simplify X. In conclusion, we have presented a novel optimization scheme for human body reconstruction, along with two simple yet powerful techniques, upstream parameter optimization and selective inverse rendering. We have achieved qualitative and quantitative improvements up to 45.5% error reduction over Simplify X baseline and concurrent work. Finally, in future work, we would like to isolate selected part better when dealing with latent and entangled parameters, incorporate kinematic constraints to the optimization, and extend our work to other domains, even beyond human bodies, as well as other parameters like color, shape, and material towards low-resource, photorealistic 3D reconstruction. And that is all for our presentation. Thank you very much for listening. Please feel free to get in touch for any questions or any discussions. Thank you.